Okay, part 2 of linear regression. We want to continue looking at the examples from the previous section. We were talking about hot chocolates and tissue boxes. Our data looked like this. These documents are on WebAssign under Resources. For reasons best known to the people running WebAssign, they've defaulted that closed. But if you click the Resources button open, you'll see all those documents there. And our scatter plot looks something like this. The correlation, the dots are very lined up, positive association obviously, so correlation, as we said, was very close to 1. It was 0.99 something if memory serves, but we can just scroll down and find out, 0.9987. Ideally I'd like a little bit more accuracy on that, but I think it'll be close enough. So now we want to quantify the line that best fits those dots, in the sense that we've talked about. The least squares regression line, the line that makes the sum of the squares of the vertical distances between blue and red smaller than it would be for any other line. It predicts for these dots better than any other line would predict, and consequently puts you on somewhat solider ground when you go to do other predictions. Notice that this has nothing to do with causation, as we talked about. If the correlation is very high, very close to 1, then we can predict with a very high degree of accuracy. Strictly speaking, the predictions will be very close for the dots we happen to have. And we make the mental leap that the predictions are probably better than they would otherwise be for other locations as well. But we'll talk about that later. If the correlation is very high, close to 1 or -1, then the dots are very lined up, and consequently the height of the dots and the height of the lines in general are very close. If the correlation is a little lower, closer to 0, if you've got like a cloud of dots, for instance, then even the best fitting line is not going to have, in general, the heights of the dots relatively close to the heights of the lines. So you can always predict. You can always find the line that will predict better than any other line would predict. But only if the correlation is very high are the predictions going to be reasonably good. And again, strictly speaking, we're talking about predictions for these particular dots. So we've talked about most of this already. And now we'll just do our calculations. So let's recap a bit, maybe blow this down a little bit. There we go. There you go, hot chocolates, tissue boxes. So our data, remember, went something like this. In computing correlation in the previous video, we found the sum of the x's, 838. We found the sum of the y's, the sum of all the y's, which was 4600. We squared the x's and added them up. We don't need that. We squared the y's and added them up. We don't need that. But of the things that we've talked about previously, we'll need the sum of the x's, the sum of the y's, the SSX, and the SSY. So there they are. And of course, correlation, our final answer. So that's what we've got to work with. And we want to find the regression line. Let's see. A little bit better maybe. So M is R times the square root of SSY over SSX. Notice, as I said, in this course there's no middle ground. Things are either relatively easy to understand and intensely tedious, and correlation is one of those. And then there are things that are a little harder to understand, but the calculations are very short. Now we're back the other way. So we'll just physically plug in everything we've computed. Again, I would like a little more accuracy on that, but we're calling the correlation 9987. It's not going to let me highlight, but there it is. SSY, which is this 342 something, divided by SSX, which is this 12,000 something. 342, 228 and 2/3, 12,061 and 2/3 with an extraneous parenthesis. Square root it times the correlation, and we get 5.3199. Now remember, we're going to use that to find B, so keep a fair degree of accuracy there. As always, try to avoid any gross intermediate rounding until you're done. Round as little as you can and as few times as you can in the middle of these processes, and we'll be a little bit more accurate. Then we'll find b by doing the mean of y minus m just found times the mean of x. Well, again, we don't necessarily have the mean exactly, but we're only a divide away from it. The mean of y was 4,600 divided by, there were 12 of them, and the mean of x was 838 divided by 12. So here I have it in that way. The mean of y minus the m we just found, answer key if you can, times the mean of x, and that's 11.8281. And there is our finished linear regression line. We're not necessarily graphing it, although I've got the graph of the red line so you can see it, but 11.8281 plus 53199x. That's a little back to front, but there you go. Don't mix up the m and the b. By the way, let's think this through logically. Worst case scenario, you've got a random cloud of dots, something worse than this, and you have computed the line that runs through those dots better than any other line would do. Worst case scenario, if you've got a random cloud of dots, the heights of the red dots, that is to say the line, are still running in between the maximum height and the minimum height, right? So worst case scenario, when you go to predict, even if correlation is very low and you've got a random cloud of dots, worst case scenario, when you go to predict for the dots you happen to have, worst case scenario, the height of the red dot at any of these horizontal locations where we've got a dot, worst case scenario, they're between the maximum y and the minimum y. If you are not seeing that at least, then you have made a mistake. In other words, you can do lousy predictions. If there was a dot that was very far away from the line, then when you went to predict, let's say, 60 hot chocolates, maybe you get something up here, maybe you get something down here, but if you're getting something under 100 or more than 600, that's a mistake. Worst case scenario, you've got to be almost literally in the ballpark. And if the dots are very lined up, they should be close. But even if the dots are not lined up, you should almost literally be in the ballpark. You know, it better be, for these particular horizontal locations, the blue ones, you should at least be getting things between max and min y. If you make a mistake on the formula, particularly if the numbers are very different as they are here, 20 to 120, 100 to 600, if you make a mistake on the formulas, you will probably know it and be able to catch it. Let me put that another way. 300,000 divided by 12,000 is a very different number from 12,000 divided by 300,000. If you get this backwards, a little common sense, and you will probably know it, because it won't even be close. For a different example, you know, those two highlighted numbers could be a little more similar to one another, but if you're at least not getting predictions in the ballpark, that's a mistake. On the other hand, if the dots are very lined up, as in this case, then the predictions should be very, very good. And that's what we'll be seeing in this particular example. So I'm going to be toggling back and forth from our data to our predictions here. But there's our predicting line, 5.3199x plus 11.8281. Now again, the y-intercept is not necessarily meaningful because we're not starting horizontally at 0 here. But nevertheless, we can do some predictings, and here they are. So I guess I don't need this page necessarily, but there's the x's and the y's. Let's blow it back up. A little more, or not. There you go. So x was hot chocolates, what we're predicting with. Y was tissue boxes, what we're predicting. And we just physically plug them in. So 121, if we run it through the formula, times that, plus that, will give us, well, to the nearest whole number, because we are talking about tissue boxes, 650. So the reality was 656. The prediction is 650. Let's look at our picture again. What are we talking about, 121? So it's this maximum dot over here. So the height of the dot is at 650, and the height of the line is just above it at 656. We're slightly overestimating for this particular location. Height of the red, 656. Height of the reality, 650. Slightly overestimating in this particular case, but still very close, 650 versus 656. Now again, there's no reason you couldn't have 2 months in which you sold 121 hot chocolates but different amounts of tissue boxes. So you can have dots above or below the dots, but there's only going to be one height of the line here. There's only going to be one red dot at this horizontal location. On the other hand, we've got 20, which I think is probably the first dot on the other end. So there it is. The reality was 116, but if we run 20 through the formula, 20 times that plus that, we get 116. So there we are. Let's see which is which here. So again, we're overestimating ever so slightly. The reality is at 116. The height of the line is at 118, which is a little bit higher. So the dot is a little bit below the line, 116 versus 118, but still very close numerically, visually. Let's see, do we have one that goes the other way? Let's maybe look at this one. So here if we go at 80, the reality is 450. Where is that? Right here, I think. So the height of the dot is at 450. And, this is one of the ones that's a little bit more pronounced. So the height of the dot is at 450, and the height of the line is a little bit below it. So what are we getting? If we plug 80 into our formula, 80 times that plus that to the nearest whole number, we get 437. So the prediction, the red line, is a little under the reality of the 450. And that was here. But still very close. Worst case scenario, I think, is probably this one, which was 50-something. So that would be, I guess, this one. So 55, we're predicting 304 if we run it through the formula, but the reality is 320. So, that height is 320, that height is 304. Still very close, and that's probably about the worst one. So very, very good. Because the correlation is so high, 0.99 something, we can see that the predictions are very close to the realities. In the case of the first, well, okay, everything I just said there. We can predict for dot X is not on our list. Now again, you're on somewhat shakier ground. You never want to forget that we're not going to talk about inference, we're not going to talk about hypothesis tests here. We could. But you never want to forget that these dots may be typical of a broader reality, or they may be very exceptional, or they may be completely cherry-picked. Again, if you have a random cloud of dots and you erase enough of them, then what remain are lined up. There's no reason in the world you can't play those games. In the real world, you can cherry-pick data. It's not ethical, but you can do it. So you always want to bear that in mind when you're predicting. It may have a basis in reality and it may not, but the best thing you can say is if you're using this line, then you are at least predicting better than any other line would predict. Even that is a kind of a presumption, but it's a solid one. So let's take a place where we don't have any dots, like say 40 here. So of course there's nothing close to a month in which we sell 40 hot chocolates, but if there were, we would sell, 200-something tissue boxes. Let's check it out. If we run 40 through our formula, times that, plus that, then we get 225. So there it is. The height of the red dot, the line, is 40 horizontally, 225 vertically, about here. Notice that 40 is in the horizontal range. It's more than 20, it's less than 120-ish. Well, it's between 121 and 20. That's the smallest, that's the biggest. For a month in which 40 hot chocolates were sold, we can predict 225 tissue box sales. Now again, there's no direct causal relationship, but this is not that mysterious either, right? It's got to do with temperature. If there were a month in which the temperature was such that you were selling 40 hot chocolates, then with a fair degree of accuracy, you could predict 225 tissue box sales. So temperature is what we call a lurking variable. We'll talk about that a bit later. Hot chocolates don't affect tissue boxes. They're both responding to temperature. There is a causal relationship there. It's just not a direct one. We can extrapolate. Extrapolate is to go beyond the ends of the data. You always want to be a little careful about this, but you can extrapolate. If you had a month in which you sold 150 hot chocolates, how many tissue boxes would you predict? Well, visually speaking, it would look something like this. If we go over here to 150 territory, we talked about this a little bit with the gorillas of the King Kong. If we continue this linear trend to horizontal 150 territory, then what height would it put us at? That's the question we're asking. Extrapolating, continuing the trend, plugging in x is bigger than the biggest x or smaller than the smallest x, off to the sides, beyond the horizontal scope here. Extrapolating. Well, just run it through and we see it's 810. So if there were a month in which you sold 150 hot chocolates, we predict 810 tissue boxes. What are we talking about? A month that is slightly colder than any of the months we happen to be looking at. Or we can extrapolate stupidly. There's no reason in the world you can't plug in 500 into this. But what assurances do we have? I can't even here. I mean, if we made this small enough to get horizontally to 500, you're not even going to see it. But we can make an effort. If you had a month in which you sold 500 hot chocolates, this territory here, horizontally at 500, vertically at who knows what. So that would be an example of stupid extrapolation, because what assurances do we have that the trend will continue to hold that far? Will the trend continue to hold to 150? Maybe it's not such a reach, but it's literally quite a reach for the trend to continue all the way over to 500, of course. Nevertheless, you can predict, it's just a question of how stupid it is. So we predict that if you sold 500 hot chocolates, you would sell 2672 tissue boxes. However, temperature is the obvious lurking variable here, and if you had a month that was so cold that you were in this kind of scenario, then obviously everybody is dead and you're not selling any hot chocolates or tissue boxes. The trend will not continue that far. So, yes, you can extrapolate wisely, you can extrapolate stupidly, you can extrapolate extra special stupidly. We'll talk about that in our next example. And I think I'll make that a separate video.